Have you ever stopped to wonder how the world came to be? The modernity of today, with all the buildings and highways that was never there before, the normalization of computers and other electronic devices, it will all lead back to minerals. Everything that supports modern living require mineral resources for production. So basically, minerals are the foundation to maintain our lifestyle today. Some of us may be wondering, what exactly are minerals? Good morning, afternoon, evening to you. We are Group 1, presenting Science of the Earth, a rocky breakdown. Your weekly deep dive into the fascinating world of Earth science. Now, let's begin our journey into unraveling the intricacies of our planet by starting off with our first segment, minerals. Minerals are typically crystalline. They are naturally occurring in organic solids. Did you know? Scientists have discovered over 4,000, or rather almost 5,000 different mineral species. But for today, I want us to divulge into this small particular group, referred to as rock-forming minerals. These are the minerals found at a rock's formation. They are a small number in all of the minerals that make up the vast majority of rocks in the Earth's crust. Some examples of these minerals are plagioclase feldspar, alkali feldspar, quartz, and many more. Now, if you go outside, you will most likely find a rock on the ground. Finding a mineral by itself is not so common. Several methods are used to identify a mineral. Such methods are using physical and chemical properties. Physical properties of minerals. Let's take this quartz for example. You can easily observe its color and conclude that it's colorless. You can also observe that it's quite glass-like in appearance. This means that its luster is virtuous. Now, when you smudge this mineral, the powder it leaves behind is white. This is how you determine its streak. Other physical properties of minerals include its hardness, its tenacity, cleavage, and crystal habit. Moving on to the chemical properties of minerals, it will involve tests and observations, like observing its solubility and melting point. Let's return to the quartz. It is a compound of 1 part silicon and 2 parts oxygen. At room temperature, it is practically insoluble to water. Now, minerals composed of atoms that are tightly bonded, like the quartz, have high melting points. For instance, quartz melts about 1,670 degrees Celsius, while gypsum, who has weak ionic bonds, melts at 145 degrees Celsius. Quartz is one of the most common in all the rock-forming minerals. They are found in many of the rocks, no matter the type. Yes, there are different classifications of rocks, but first, let's start our second segment with defining the term rock.
From minerals to rocks, the building blocks of our world, from the towering peaks that pierce the sky to the hidden depths of the earth, rocks are the silent witnesses to our planet's history. They tell tales of ancient oceans, fiery volcanoes, and the relentless forces of erosion. It is now my turn to speak of their own tales. What are rocks? Rocks are the building blocks of our planet. They are naturally formed resources which are made up of minerals. And they are like the tiny pieces of a puzzle that when you join them together, you get a larger picture. If you think of it like this, rocks are the building blocks of our planet, and minerals are the building blocks of rocks. And when we speak of rocks, there are 3 main categories: igneous, sedimentary, and lastly, metamorphic. Deep beneath the Earth's surface, there's a fiery liquid called magma, and when this magma rises and cools, we get igneous rocks. Igneous rocks can be categorized into 2 types: extrusive and intrusive, depending on where it has cooled. But this is not where the story ends, for over millions of years can pass by and rocks can be transformed within that period of time. Weathering can break these rocks down to their small versions, and these small versions can be broken down further, and they can be transported by the wind, water, and ice. And eventually, they would settle down, and they would compact, and eventually, they would cement together to form sedimentary rocks. Well, deep beneath the Earth's surface, where we have returned once more, there is intense pressure and heat, and these conditions can transform rocks, no matter their category, be it igneous, sedimentary, or metamorphic itself. When they are subjected to these conditions, they become transformed under the process of metamorphism. They are formed without undergoing the process of melting or experiencing recrystallization. The impact of stress on rocks. Stress in geological terms is the force applied on a rock per unit area. There are three types of stress: compression, tension, and shear stress. These forces can cause rocks to deform, fracture, or even metamorphose. The type of stress a rock experiences can determine its behavior and the type of geological formations it forms. For example, compression can lead to the formation of mountains, while tension can create rift valleys. The formation of rocks is a continuous cycle known as the rock cycle. It's in the name. The rock cycle involves various transformations of one type of rock into another using various geological processes.
Now that the tales of stone have been spoken, remember this journey that rocks have silently taken through the eons. Think of how nearly every piece of stone, rock, or pebble you see has had a part in the vast formations that decorate the surface of our planet. But before my segment here ends, have you noticed how I began the rock cycle with process 2? Well, before the cycle can begin, there's an important process that must occur to provide the materials for the rest of the cycle, and that is
weathering. Weathering is the process of earthy materials decomposing. It can be found constantly happening everywhere on the Earth's surface. Rocks and minerals, like these, undergo weathering due to the natural elements, whether it be through the rain, the cold of winter, exposure to the atmosphere, or even animals, like a prairie dog or a rabbit, can contribute as agents of this wondrous phenomenon.
Now, while this happens, erosion begins and displaces the weathered down materials by use of erosive agents, such as wind or water, and begins an arduous journey in which during the transportation, they slowly erode over time. A lot of these material deposits also influence the process of sedimentation.
Another agent, gravity, contributes to the erosion through running water and goes hand in hand with the weathering of the earth.
Through this process, movement of the rocks and soil due to water is produced. Then, if you add gravity to the mix, rockfalls, landslides, and mudflows become the result.
The shifting of stone in the earth varies greatly for each individual rock, whether it be small or large. However, have you ever wondered how it would work beneath the surface of the Earth? There's one theory that scientists have studied that describes exactly that. And that is
Continental drift theory. Alfred Wegener proposed the continental drift theory in the early 20th century. He suggested that the continents were once part of a single supercontinent called Pangaea, which later broke apart. The continents then drifted to their current positions. However, many scientists at the time rejected his theory due to a lack of solid evidence. Wegener, a meteorologist rather than a geologist, also inaccurately suggested that Earth's rotation caused the continents to move. Evidence for continental drift. Today, there is significant evidence supporting continental drift. One key example is the presence of similar fossils on continents now separated by oceans. For instance, fossils of the Mesosaurus, a freshwater reptile, have been found in both Brazil and Africa, indicating these continents were once connected, as the Mesosaurus could not have crossed the South Atlantic Ocean. Seafloor spreading. Seafloor spreading occurs at mid-ocean ridges, where magma rises and creates new oceanic crust. This process, first discovered by Harry H. Hess in the mid-20th century, pushes older seafloor away from the ridge, expanding the ocean basin. Sonar mapping after World War II revealed that areas near mid-ocean ridges were warmer, suggesting magma activity. This finding supported the idea of shifting continents. Structure and evolution of ocean basins. Ocean basins cover about 70% of Earth's surface and are shaped by tectonic plate movements. Features include mid-ocean ridges, abyssal plains, seamounts, and trenches. Ocean basins form through seafloor spreading and shrink through subduction, where an oceanic plate is forced under another plate, creating deep trenches like the Java Trench. The breakup of Pangaea around 200 million years ago led to the formation of the Atlantic and the Indian Oceans. Meanwhile, the Pacific Basin is shrinking due to ongoing subduction. Geologic features. Tectonic plate movement shapes Earth's surface, creating folds, faults, trenches, volcanoes, rift valleys, and mountain ranges. Folds and faults. Convergent boundaries cause the Earth's crust to fold, forming mountain ranges like the Himalayas. Faults occur when plates slide past each other, often resulting in earthquakes. Trenches. Formed at subduction zones, where one plate dives beneath another. An example is the Mariana Trench, created as the Pacific Plate subducts under the Mariana Plate. Volcanoes. Found at divergent boundaries or mid-ocean ridges and convergent boundaries or subduction zones. The Pacific Ring of Fire is a prime example of volcanic activity due to subduction. Rift valleys. Formed at divergent boundaries with continental plates. As plates pull apart, the crust fractures, creating valleys like the East African Rift. Mountain ranges. Created when two continental plates collide.
Look at all those greenery. The mountains. Them slope. My name is Arevalo, and in this segment I will teach you about the Earth and its layers, from the crust you all see here to the very bottom to the core of the planet. Here we are, the classic, the layers of the Earth. Of course, the three main components: the crust, the mantle, and the core. Let's dive into it, shall we? Here we are at the very top, the crust, the continental and the oceanic crust, the two types. 69 kilometers at its thickest and at its most intense, 7,000 degrees Fahrenheit and above. There it is, Taal, the famous volcanoes here in the Philippines. What are we doing here? So we'll also be talking about the second layer of the earth, the mantle. Let's go there now. Now here we are, the second layer, the mantle. Very well known, I might say. At its deepest, 29,000 kilometers deep. Whew. It has two times just like the crust, with varying levels of viscosity the deeper it gets. In here, the temperatures reaches up to 18,000 degrees Fahrenheit. Very yikes. I wouldn't want to live down there, no. Now our planet has a heart of iron, may I say. It is 24,000 kilometers in diameter. Jeez. And it's mainly composed of iron and nickel. It's mainly the accepted reason as to why the Earth has its magnetic fields. The pressure there is so immense that it's virtually solid even at such a molten state. Can't you believe that? Liquids that are now acting like solids. What a crazy world we're in. Sure, it may be one of the reasons why we humans have survived solar flares. That's some scary stuff. Look at those clouds. Now, another proper question that gets asked when talking about the layers of the earth is the temperature down there. Like, gee, how does it get so hot down there? Now let me tell you why. It's when the earth was a baby, it was a very hostile place. Just look at that thing, it's filled with lava. Plus we can't forget about what makes up the mantle and the core. There's so much radiation there that Earth pretty much has a oven for a heart. Not just iron, an oven. I wouldn't want to live down there. No.
The Earth is a wildly complicated subject. From its extremes to its mean, all matter of the Earth has a reason for how and why it is the way it is. We humans are but a speck of dust surrounding and covering the surface of the huge ball of rock and dirt we call home. It is why it is fascinating to learn more about our planet. From the rocks that make up the mountains to the glowing red magma spewed by volcanoes. We realize that our planet will not look like the way it is in a few million years from now on, but we can rest easy knowing the fascinating things that happen under here.